Hello guys, so this will be our new topic for this week. It's about Laplace transform and inverse Laplace transform. So before that, we're going to have a short recap of our previous topic. So previously we have started with the control system. So this is the introduction of the control system. So a control system is a system which provides the desired response by controlling the output. So the following figure shows the simple block diagram of a control system. So as you can see here, this material is different from the book that I have provided you. This is a much simpler material, which I will be I will be giving also as a part of the material for this subject. So this is the basic block diagram. So at the left side, you have the input with an arrow moving to the right, and with the box at the middle, which is the control system. So the control system here could be any process or function. Then from the control system to the right side, you have an arrow, and that represents the output. So input left, output right. So here the control system is represented by a single block, and since the output is controlled by varying the input, the control system got this name. So we will vary this input with some mechanism, and in the next section, so we are going to have the open loop and the closed loop control system. So example of a control system, we have the traffic light control system and the washing machine. So traffic lights control system is an example of control system. So here a sequence of input signal is applied to this control system, and the output is one of the three lights that will be on for some duration of time. So during this time, the other two lights will be off. So based on the traffic study at a particular junction, the on and off times of the lights can be determined. So accordingly, the input signal controls the output. So the traffic lights control system operates on time basis. So we have different classifications of control systems. So based on the parameters, we can classify the control systems into the following ways. One, you could have a classification as continuous time and discrete time control systems. So how they are classified is based on the type of signal used. So when we call continuous time, they are using analog signal, and when we call discrete time, they are using two types of signals. It could be the digital signals, which has high low, and positive high and negative low. So in continuous time control systems, all the signals are continuous in time, but in discrete time control systems, there exists one or more discrete time signals. So another classification is the seesaw control system and MIMO control system. So seesaw means single input, single output. So just like this diagram, single input and single output. So that's a seesaw. So if you have a MIMO, multiple inputs, multiple outputs, so you have several inputs going to the control system, or you have several outputs from your control system. So that's MIMO. Then you also have a classification of control system as open loop and the closed loop. So if we say open loop, so there is no feedback. So if we say closed loop, there is a feedback path. For example, here we have an open loop. So input, controller, then the output of the controller is the activating signal, which is the input of the plant, and the plant has the output. So we have done with this one. So the next diagram is the closed loop control system. So here we have a feedback path. So this one, so this is the feedback path. So we have a feedback elements and a feedback signal. So that's the difference between the open loop and the closed loop. So the error detector produces an error signal, which is the difference between the input and the feedback signal. This feedback signal is obtained from the block or from the feedback elements, then by considering the output of the overall system as an input to this block. So instead of the direct input, the error signal is applied as an input to a controller. So for example, aircon, in your assignment, you have there an answer of automatic water heater, no? Or water cooler. So for example, the input here is the desired water temperature. Then you have here the water system, the heater. For example, it is a heating system. So the heater, then this is the uh, water heater system. So the output, for example, the actual target or the target temperature is 50 degrees Celsius. Then the actual is 40 degrees Celsius. So the difference of 10 degrees Celsius is fed back to your input or to your heating system. So that 10 degrees difference is called the error signal or the feedback signal. So here is a table of the difference between the open loop control system and the closed loop control system. So in open loop control system, the control action is independent of the desired output. So whatever is the output, it doesn't affect the control. Then feedback path is not present. Then these are also called as non-feedback control system. Easy to design, economical, and inaccurate. So for a closed loop control system, the control action is dependent of the desired output, because if the output is above or below the target, so the control is changed. Then the feedback path is present. Then there's also feedback control system. Difficult to design. These are costlier and accurate. So let's go to types of feedback. No? So if either the output or some part of the output is returned to the input side and utilized as part of the input system or the system input, then it is known as feedback. So feedback plays an important role in order to improve the performance of the control systems. And in this chapter, we are going to discuss the types of feedbacks and the effects of feedback. So there are two types of feedback. So we are going to focus, or we're going to deal with the positive feedback and the negative feedback. So as you can see here, we have a closed loop control system. So in this case, we have a positive feedback. So meaning the signal from the output going back to the input is positive. So we have here a positive sign. So that's a positive feedback. So the positive feedback adds the reference input RS and the feedback output. So the following figure shows a block diagram of the positive feedback control system. So the feedback here is added back to the input with a plus sign. So that's a positive feedback. So if we get the transfer function of this positive feedback, the t here, which is the transfer function, don't worry, the transfer function will be discussed later, no, or in the upcoming topic. So just take note of this one. For a positive feedback, the transfer function is given as g, which is the value of your control system here, divided by 1 minus the product of your g and h. So for a positive feedback, the sign in between is a negative. So if the transfer function has a 1 minus gh, that means the feedback is positive. So take note of that one. So t here is the transfer function or the overall gain of the positive feedback control system. G is the open loop gain, which is a function of frequency, and h is the gain of the feedback path, which is a function of frequency also. So negative feedback. So negative feedback reduces the error between the reference input RS and the system output. So the following figure shows the block diagram of the negative feedback control system. So negative feedback, so you can see here, the entering signal is negative, so it's negative feedback. And for the formula, the transfer function has a positive denominator. So the transfer function is equal to G divided by the quantity 1 plus GH. So T is the transfer function, G is the open loop gain, and H is the gain of the feedback path. So effects of the feedback. Now, for example here, the equation 2. Equation 2 is for negative feedback control system. So from equation 2, we can say that the overall gain of the negative feedback control loop control system is the ratio of G and 1 plus GH. So the overall gain may increase or decrease depending on the value of 1 plus GH. So if the value of 1 plus GH is less than 1, then the overall gain increases. In this case, GH value is negative because the gain of the feedback path is negative. So if the value of the 1 plus GH is greater than 1, then the overall gain decreases. And in this case, the GH value is positive because the gain of the feedback path is positive. So in general, G and H are functions of frequency. So the feedback will increase the overall gain of the system in one frequency range and decrease in the other frequency range. So what is the effect of feedback on sensitivity? So here it is presented as that sensitivity of the overall gain of feedback closed loop control system to the variation in the open loop gain is defined as, so we have here the percentage change in T, which is the transfer function, divided by the percentage change in G. So we have lambda T over T divided by lambda G over G. So where lambda T is incremental change in T due to incremental change in G. Or we can rewrite the formula as the sensitivity is equal to lambda T over lambda G multiplied by G over T. So here's our favorite part. We are going to do partial differentiation. So if you get the partial differentiation of this formula because of the lambda, this is the partial differentiation method. So you get the partial differentiation of lambda T over lambda J. So we have 1 over 1 plus GH squared. So from equation 2, you will get G over T is equal to 1 plus G over 1 plus GH. So substitute equation 5 and equation 6 in equation 4. We have the formula for sensitivity as 1 divided by the quantity 1 plus GH squared times 1 plus GH. So common denominator and numerator, so cancel 1. So the answer left, or the quantities left, is 1 over 1 plus GH. So we get the sensitivity of the overall gain of a closed loop control system as the reciprocal of 1 plus GH. So sensitivity will increase or decrease depending on the value of the quantity 1 plus GH. So if the value is less than 1, then sensitivity increase. So if the value is greater than 1, then the sensitivity decreases. So what is the effect of feedback on stability? So a system is said to be stable if the output is under control. Otherwise, it is said to be unstable. So what's the purpose of stability? Now, for example, if you're going to create a project and if you want to have an input, for example, amplifier, if you have an input 1 volts, and you want that to increase since it is amplifier, so the output should be 5 volts. So if it is not stable, so you can get an output of less than 5 volts or more than 5 volts. So we need to check its stability. So if you're going to design a project, you need it to be stable. Because if that amplifier is used to power a different unit, then the unit requires a stable voltage, then if it is giving a high voltage required or higher more than the required of the unit, then the unit will be destroyed. So if you are going to design, we need it to be stable. So in equation 2, if the denominator value is 0, for example, GH is equal to -1, so 1 minus 1, so that's 0. So then the output of the control system will be infinite. So any number divided by 0 is infinite. So the control system become unstable. So therefore, you have to properly choose the feedback in order to make the control system stable. So we should not have a G times H equal to -1. So effect of feedback on noise. So to know the effect of feedback on noise, let us compare the transfer function relations with and without feedback due to noise signal alone. So consider an open loop control system with noise signals as shown below. So here we have an open loop control system. So we have here an input RS. Then we have here a process GA. Then in between GA and J sub A and J sub B, we have here noise entering the signal. So NS. Then you have here the output CS. So the open loop transfer function due to noise is signal alone is given as CS over NS is equal to GB. So if we're going to consider this as a open loop control system, so if you get the transfer function is defined as the output divided by the input. So the output here is CS divided by the input in S, so that is equal to GB. So you get this equation. So this is obtained by making the other RS equal to, so this is one RS equal to 0. So consider a closed loop control system with noise signal as shown. So if the control system has no feedback, so automatically this part, this original input becomes lost. So the transfer function now becomes effect of or the ratio of the output and the noise only. So but if it is a control or a closed loop control system, so here we have the same scenario but it has a feedback, so the noise is entering. The closed loop transfer function becomes CS over NS, which is equal to G sub B divided by 1 plus G sub A times G sub B times H. So it is obtained by making the other input RS equal to 0. So in the closed loop control system, the gain due to noise signal is decreased by a factor of 1 plus G sub A, G sub B, and H, provided that the term 1 plus G sub A, G sub B, and H is greater than 1. So you have here mathematical models. So the control systems can be represented with a set of mathematical equations known as the mathematical models. So these models are useful for analysis and design of control systems. So analysis of control systems means finding the output when we know the input and the mathematical model. So design of control system means finding the mathematical model when we know the input and the output. So the following models are mostly used. One, we have differential equation model. Second, we have transfer function model, and third one is the state space model. So let's first have the two models in this chapter, then the other two is the later part of the class. So differential equation model. So differential equation model is a time domain mathematical model of control systems. So follow the steps for differential equation model. So apply basic laws to the given control system and get the differential equation in terms of input and output while limiting the intermediate variables. So example here is an electrical circuit. So you have here an input VI, positive, negative. Then we have here current entering, which is I. So then we have here a resistor R, an inductor L, and a capacitor C. So this is a loop. So if we are going to create a loop, so we have here a loop. So a loop here. No? So applying the mesh equation for the circuit, we can get that the input voltage is equal to Ri. Ri is the resistance here times the current plus the inductance times the derivative of I with respect to time plus the output voltage. So since this is voltage, so using the Ohm's law, so we have VIR so voltage equal to current times resistance. So we have here IR, we have I. So since it is inductance, so we multiply it with the first derivative of your current with respect to time, again plus the voltage drop output here. So we do not get the voltage drop across C since this is parallel. So we assume that the voltage drop here is also the same as the voltage drop here. So substitute the current passing through the capacitor I is equal to C derivative of the output voltage with respect to time in the above equation. So we can get VI is equal to RC dVO over dt. So since I here is given as C dVO over dt, so we have here d squared VO over dt squared plus VO. So rearranging the formula, we can get d squared VO divided by or over dt squared plus the ratio of RL times dVO over dt plus 1 over LC VO is equal to 1 over LC VI. Now this equation is a differential equation. So this is the first model of writing our control system. So if you have here a differential equation, you can represent this as a control system. So this model or this equation represents this electrical network. So next we have the transfer function. Now transfer function model is an S-domain mathematical model of control system. So S-domain, so meaning frequency domain. So if you have S-domain, that is frequency domain. So to get the frequency domain, you are going to convert time domain to Laplace transform. So the transfer function of a linear time invariant system, or the LTI, is defined as the ratio of the Laplace transform of the output and the Laplace transform of the input. So assuming that all initial conditions are 0. So in this case, we should have, or by this time, we should have learned how to get the Laplace transform of a time domain. So if xt and yt are the input and the output of an LTI system, then the corresponding Laplace transforms are x, s, and ys. So take note that for simplicity, if we are going to have a time domain system, we represent them with a small letter. So for example, xt. So we have here small letter x, and a function of t, which is time domain. So if we are going to get the Laplace for that and convert it into S domain or frequency domain, we use a capital letter. So we have here capital letter X, then a function of S or frequency. So for yt, that becomes ys. So therefore, the transfer function of LTI system is equal to the ratio of ys and xs. So transfer function is equal to ys over xs. So the transfer function model of an LTI system is shown in the following figure. So xs, which is the input, so input divided by the output divided by the input. So this will be the value of your system. So example, we are going to convert a differential equation which is in time domain of an electrical system to its Laplace or its frequency domain. So if you could recall in the uh, first model, so we have here a differential equation. So apply Laplace transform to both sides. So if you could recall how to get Laplace transform from t domain to frequency domain, so you can get that d squared vo over dt squared is equal to e squared vos. Then this part so simplifying, we have here like we have VOS and the right side we have VIS. So the VO, the output here divided by the input, so that's the transfer function. So if we get the transfer function, that would be 1 over LC divided by the quantity is squared plus RLS plus 1 over LC, where VIS is the Laplace transform of the input VI and VOS is the Laplace transform of the output VO. You can change also, so capital V, capital V. So the above equation is the transfer function of the second order electrical system. So the transfer function model of the system is shown below. So in terms of the frequency domain, so the VIS here, the input, and the VOS serves the output. So the transfer function is 1 over LC divided by S squared plus R over L times S plus 1 over LC. So here we show a second order electrical system with the block having the same transfer function, and the block has an input VIS and an output VOS. So before we proceed to this next few topics, we are going to discuss again Laplace transform. So what is Laplace transform? So based on the material that I provided you last time, so here is a definition of a Laplace transform. So Laplace transform is a standard notation in dynamics and control system. It converts mathematics to algebraic operations and advantageous for block diagram analysis. So example. Oh, by the way, this is the standard formula for a Laplace transform. So if you have a function of t which is a time domain, the Laplace transform of this function is given as the integral of your ft multiplied by e to the negative st dt from 0 to positive infinity. So in this case, we're going to use only the positive half of your signal. But in reality, if you're going to get the Laplace transform, you're going to start with the negative infinity to positive infinity. But in this case, we can also just take the positive part of that signal. So we have 0 to infinity. So you get the integral of function, of whatever function it is, multiplied by e to the negative st dt. So example, here. So for example, you have a function, a function of t equal to a mu t. What man? So function of t is equal to a. So you get the Laplace of the function of t is just equal to getting the Laplace of a. So to get the Laplace of a, so we have here a, or Laplace of a is the integral of a times e to the negative st dt from 0 to infinity. So since a here is a constant, so we move a outside and we get the integral of e to the negative st. So applying the rules of integral, so we have a result as negative a over s times e to the negative st from 0 to infinity. So if you're going to evaluate this this equation, so evaluate this one, the rules of integral. So if we substitute infinity to s here, I mean t, so e to the s times e to the negative st, so e, which is a Euler's number with an negative infinity, that is 0. So 0 times negative a to the s, so that would become 0. So 0 here minus, if that is to the negative 0 t, so s times 0, 0, e to the negative 0 is 1. So 1, so 1 times e to the s. So 0 minus the negative e to the s, the answer is e over s. So this is for example number 1. The example number 2, so the function is e to the bt. So you get the integral of e to the bt times e to the st. So i-combine lang mo since same ang ilang base. So you have here e to the negative b plus s times t dt. So you apply integral formula here. So you have 1 over b plus s times e to the negative b plus s t. Then evaluate this equation from 0 to infinity. So we have here 1 over s plus b. So another example, So in this example, the function is derivative, so first order derivative, so f prime. So the Laplace transform of f prime is equal to uh, derivative of f over dt times e to the negative st dt. So that will become s lf minus f sub 0. So if the initial here is 0, so automatic your answer is s l f. So usually define f of 0 is equal to 0, so the answer here is s l f. So other transforms, if you have a second order derivative, if you get the Laplace transform of a second order derivative, you have here s squared fs minus sf0 minus the f prime of 0. So usually if this is equal to 0 and this is also equal to 0, the answer here is s squared f s. So in our concept notes, or in our notes, let's say this is secant squared of VO over dt squared. So if we get the Laplace transform of this one, in our answer we have VO s times s squared, or that is equal to s squared VO s. So we assume that this s f sub 0 is 0 and f prime is also 0. But if this is not 0, so we can have a minus next to s and so on. So this is also in your handout now. So this is the process in solving the Laplace. And there's this one. Now this is the table that you can use to solve, or in finding the Laplace transform. So if you have a unit impulse, increase this one. So if you have a unit impulse, where is the unit impulse? So unit impulse, if you get the Laplace, that's 1. So if you have unit step, so make a unit impulse. For example, nakay signal. So unit impulse is an impulse signal. So if you have a signal here, then this is your 0, this is your negative 1, this is your positive 1, then you have here negative infinity, this is positive infinity. So if you have impulse, so ang iyang value positive 1 siya at 0. So the rest here are 0 na. So muna unit impulse. Usa lang iyang value for 1, which is at x is equal to 0. So to get a Laplace for a unit impulse, so since usa lang siya 1, so the answer is 1. Now for a unit step, so the Laplace transform for a unit step, which is given as st, is 1 over s. So what is a unit step? So for example, you have here a signal. Same ra gyapon ganyan, no? So nakay 0 diri. 1, 2, and so on. So positive infinity. And here negative 1, negative 2, and so on until negative infinity. So make a unit step from left side of the 0, which means negative infinity, negative 2, and negative 1, these are 0. But at 0, the value of your y is 1. The value at 1, the value is also at 1. At 2, the value is also at 1. So katon siya i-graph, so nga na siya So ato siya i-graph, straight to siya diha. So mo nang unit step. Kay kini siya 0, pag abot sa 0 ni 1 siya, and so on. So that's a unit step. So if you get a Laplace transform of a unit step, the answer is 1 over s. So next we have here ramp. So ramp is also different signal. For example, same ganiha. You have here a 0, 1, 2, and this is 1, negative 1, negative infinity, plus infinity. Ang ramp, for 0, 0. For 1, the value is also 1. For 2, the y value is also 2. So as you can see, if you're going to graph this one, pasaka siya, marsya og hagdan o ramp. Pasaka. Okay, kung pila yung value sa imong x, mo say, for example, this is your x and this is your y. Kung sa value sa x mo say value sa yang y. So that's the ramp. So if you have a ramp, which is given as t, the Laplace transform of a ramp is 1 over s squared. Okay, may erase. So if you have t to the n minus 1, so that's n minus 1 factorial over s to the n. So if you have e negative bt, so same with our example, itong example number 2, so we have 1 over s plus b. So b here could be any number, no? So for example, if you have e to the negative 3t, if that is your function t, no? If we get the Laplace of that one, the Laplace of e to the negative 3t, that would become 1 over s plus 3. So very simple, no? If you have this table, so use this as reference. So b here is any number. Then you have here another, no? So take note of this sign. So for example, you have a function ft is equal to sine of 3t. So what is the Laplace of this one? So the Laplace transform of sine of 3t based on this formula is equal to omega over s squared plus omega squared. So since our omega is equal to 3, so that would become 3 over s squared plus 3 squared, which is equal to 3 over s squared plus 9. So this is our Laplace transform of sine 3t. So if it is cosine, so cosine na pod ft is equal to, example, cosine of 2t. So that would become, if they are going to get the Laplace of cosine 2t, that would become s over s squared plus omega squared, which is 2, so 2 squared. That will become s over s squared plus 4. So this is our Laplace transform of cosine to t. So familiarize with the other values here in the formula na, in the table. Also this one. So here we have at the bottom 24, 26 the formula for differential equations. So first order, second order, or any order no n. So yun sa siya yung formula. So you have here an ordinary differential equation. So first order derivative 5 dy over dt plus 4y is equal to 2. Then unlike in our example, ang y sub 0 niya diri is na value which is 1. So first we are going to get the transfer function. So what is the Laplace? So find Laplace of 5 dy over dt plus 4y, which is equal to 2. So first you're going to take the Laplace transfer of both sides. So kini unahan na to, kini nga side. So 5 times the Laplace of dy dt. So if you're going to go back to your formula, so dy dt is dire no, kini siya df over dt. So if that is y, so this mahimog sa isang y. So s, so since this is first order man, so only s times ys minus 1. So since itong formula, for example, that is dy dt, so the Laplace transform of dy dt is equal to s y s minus y 0. So you have here s ys minus y sub 0. So since y sub 0 has a value of 1, so we have here minus 1. Then plus the Laplace transform of this equation for y. So y siya small letter, may mo siyang capital letter ys. So diri we have here 2. So 2 here as an imaginary partner, that is 2 mu t. So mu t, if you're going back to your table, so mu t is this one. So st is also known as mu t. So nasa 2 times mu t. So if we get the Laplace of mu t, that is 1 over s. So we have here 2 times, so yun siya, that is equal to 2 times 1 over s, or that is 2 over s. So we have 5 times sys minus 1 plus 4ys is equal to 2. So if you're going to simplify this one, that will become 5 sys minus 5 plus 4ys is equal to 2 over s. So i-combine lang na ito ang mga ys. So that will become 5s ys plus 4ys is equal to 2 over s. So naman kay negative 5 diri, if we transfer that from left to right, may mo siyang positive 5. So remove ys, so we have ys times 5s plus 4 is equal to, so we can combine this one, no? So we have 5s plus 2 over s. So our target here is to get the output man, which is ys. So we have ys on the left side, then transfer this one to the right side. So that will become 5s plus 2 over s divided by 5s plus 4. So muna siyang result is equal to this one. So this is our Laplace equivalent, or the frequency domain, no? Equivalent of our differential equation. But here, if you are going to solve ODE, dapat kung time domain siya, ang ato pong answer is time domain. So from this one, ato siya i-convert balik into time domain by getting the inverse, kaya siya, muna ang inverse Laplace transform. So inverse Laplace transform, L negative 1. So that's from capital YS, may mo siyang small yt. So L negative 1 is equal to 5s plus 2 over s 5s plus 4. So from table 3.11, what's 3.11? 3.1 line 11. 3.1 line 11 here. This one. So we can get, so 3.1 line 11, yt is equal to 0.5 plus 0.5 e to the 0.8 t. So we have here another example of third order derivative, wherein it's y sub 0, y prime 0, and y double prime 0 is equal to 0. So this means the system is at rest, so from 0. So d cubed, then d squared, and dy. So just follow the steps. So to find the transient response for yt, take the Laplace transform, then factor using partial fraction decomposition, then take the inverse Laplace transform. So from this given equation, you would have, if we get the Laplace of this equation, that would be s cubed ys plus 6s squared ys plus 11 11s ys plus 6ys is equal to 4 over s. And after that, we are going to combine several the same base. So we arrive at this one, ys equal to 4 over s cubed plus 6s squared plus 11s plus 6. Then you factor the denominator of ys. So this is the one of the method in finding the inverse Laplace. Now we're going to have that one later. So i-factor out lang nato ng s cubed plus 6 squared plus 11s plus 6. So that is equal to s plus 1 times s plus 2 times s plus 3. Then using partial fraction decomposition, you have alpha 1 over s plus alpha 2 over s plus 1 plus alpha 3 over s plus 2, then alpha 4 plus over s plus 3. Then using the partial fraction method, you will arrive at this formula. Yt is equal to 2 over 3 minus 2e negative t plus 2e negative 2t minus 2 over 3e to the negative 3t. Then t here is from 0 to positive infinity. So we have yt is equal to 2 over 3. So if you're going to consider this one, So at t is equal to 0 and y equal to 0 is 0. So since this is at rest. So these following methods are finding the inverse Laplace na. Okay, inverse Laplace. So regarding the inverse Laplace, we are going to make use of our the nice control system book that I have provided you earlier. So we are going to frequency domain. So this is the formula of the Laplace transform and the standard Laplace transform table. So this one so this is the impulse and this is the unit step. This is the ramp and this one is exponentiation. This one exponentiation, sine and the cosine. So same example that we have in the other presentation. So here we're going to focus with the inverse Laplace transform. So take note of this table 2.2, no, the Laplace transform theorems. So number one is the definition of the Laplace transform. So if you have a function t, then you get the Laplace transform of function t. The answer is f of s. And the formula is 0 to infinity, the integral of ft times e to the negative st dt. So if you have a function or a constant k, so if you're a k, no? So what? So if you have a k here, then multiply the function of t. So that is kfs. So example, so example. So for example, you have a function. Okay, for example, you have a function denoted by e to negative 2t. So if we get the Laplace transform of e to the negative 2t, that will become 1 over s plus 2. Since we have here a negative 2 man, so our denominator is 2t. So if we follow the definition, so the Laplace of our function is equal to the derivative from 0 to infinity of your ft multiplied by e to the negative st dt. So muli ang number 1. So for number 2, so if you have an L or you have here a function, a function of t which is equal to 2 e to the negative 2t. So according to the second theorem, that is just equal to 2 times the Laplace transform of e to the negative 2t. So 2 times 1 over s plus 2. So the Laplace transform of this function will become fs is equal to 2 over s plus 2. So manig pasabot sa linearity theorem. So if you have two functions nga gi-add, you can solve the Laplace transform by getting the first Laplace transform of f1, then add with f2. So nga lang, no? Then frequency shift theorem, if you have a function multiplied by e to the negative at, so ang yang s sad siya na is mo shift sad so so what does it means? So what does it mean things for? So for example, you have a function, same ganyan number. For example, let's have this example number 4. Okay. So for example, you have a function equal to e to the negative 3t. So if we get the Laplace transform of e to the negative 3t, So that would be 1 over s plus 3. If you have this example, ft is equal to e negative 3t, hindi na siya sumpay nga e the negative 2t. So if you get the Laplace, okay, Laplace transform of your function, so that would be e to the negative, so that would be f as a function of s plus 2. So if this is your f of s, if this is your f of s, what does this mean? So it means nga imuhang s i-shift nimo og plus 2. So in this case 1 over ang s nimo imong pulihan og s plus 2. So mahimo na siyang s plus 2 plus 3. So mahimo siyang 1 over s plus 5. So this is your Laplace transform. Gi-shift siya og negative 2. So negative 2 mahimo siyang plus 2. So mahimo siyang s plus 5. So kaya s plus 5. How to end this recording?